On any clear night, the moon hangs in the sky, a pale, luminous guardian of the darkness. For thousands of years, humans have gazed upon it, tracking its motions, measuring its phases, and imagining its silent beauty. We know its familiar features, the smooth lunar seas called Maria, dark plains that stretch like blackened oceans across the lunar surface, the sharp, jagged rims of craters formed by ancient collisions, the soft grey regolith that blankets it like dusted silk. The moon has been our clock, our calendar, our silent companion, marking the passing of nights and months, inspiring poets, philosophers and astronomers alike. Yet for all our careful observation, for all the probes, landings and photographs, there remains a hemisphere we cannot see from Earth, the far side of the moon. A side that hides in permanent shadow from our perspective, cloaked not in darkness but in ignorance. It is a landscape alien in its familiarity, a reminder that the universe, even at its closest, contains mysteries that evade our grasp. The far side is not merely another moon face, it is an enigma that challenges our understanding of nature, time and history. Unlike the side that turns toward us, marked by smooth plains and scattered craters, the far side is rough, mountainous and cratered, a chaotic tapestry of impact scars older and more numerous than those we see from Earth. And yet, there is an order to this chaos, an intricate pattern that hints at forces beyond simple collisions. Symmetrical formations, rectilinear ridges, dome-like protrusions that rise in shapes almost geometric, and, most compelling of all, the mass concentrations, or mascons, that distort gravity in ways scientists still struggle to explain. These anomalies suggest that beneath the lunar surface lies a record not just of celestial bombardments, but perhaps of something more deliberate, more profound. Consider the largest basin on the Moon, the South Pole Aitken Basin, stretching nearly 2,500 kilometers in diameter, making it the largest known impact structure in the entire solar system. Its size alone should be extraordinary enough to command our awe. But even here, mysteries multiply. The composition of its crust does not match our models. Mineral deposits seem arranged in ways inconsistent with standard impact theories. NASA's Lunar Reconnaissance Orbiter and China's Chang'e 4 mission have sent back high-resolution data revealing a far-side landscape that is uneven, oddly aligned, and structured in ways that suggest a history not entirely governed by chance. Some features appear almost artificial in their precision, raising questions that science cannot yet answer. Are these patterns merely geological, or are they echoes of a force or event unknown to humanity? It is tempting to dismiss such thoughts as mere speculation. After all, the moon is a celestial body, governed by physics, gravity, and the slow patience of time. Yet, even the most rational of observers cannot ignore the philosophical weight of what the far side represents. Here, in the shadows, the moon preserves a record of the universe older than any civilization. It is both familiar and alien, close enough for humans to touch in imagination, yet distant enough to resist understanding. The far side reminds us that knowledge is never complete, that even the objects we think we know best can harbor secrets we are not yet ready to comprehend. From Earth, the moon appears as a constant, a fixed point in a dark sky. We forget that it moves, that it is caught in a delicate gravitational ballet with our planet and the sun, traveling through space at more than 2,200 miles per hour, yet always showing us the same face. Its seeming constancy is an illusion, masking the far-side complexity that only spacecraft can reveal. Every ridge, crater and shadow on that hidden hemisphere is a page in a story billions of years in the making, a story of violent impacts, molten interiors, and slow, inexorable changes. And woven through that story is the puzzle of mascons, dense concentrations of mass that pull and tug in ways that affect lunar orbit, satellite trajectories, and perhaps even Earth itself. What does it mean that our closest celestial neighbor holds such secrets? Philosophers have long pondered the relationship between knowledge and perception, between what is seen and what remains hidden. The moon, in its silent vigil, becomes a mirror not just of our night sky, but of our curiosity. It challenges the assumption that proximity guarantees understanding. It asks us to consider the limits of human knowledge and the humility required to accept that some truths may be revealed only in fragments through patient observation, careful measurement, and imagination guided by reason. Recent missions have opened a window into this unseen world. The Lunar Reconnaissance Orbiter has mapped the far side in unprecedented detail, revealing not just craters, but aligned ridges, concentric formations, and subtle irregularities in gravity. Chang'e 4, the Chinese robotic lander and rover, has studied the von Karman crater at the heart of the South Pole Aitken Basin, uncovering mineral anomalies that hint at a complex geological history. When these data points are considered together, a pattern emerges, not one that can yet be explained with confidence, but one that tantalizes with possibility. Could these formations be purely natural, the result of ancient collisions and volcanic activity? Or do they suggest a history we have yet to imagine, an impact engineering on a scale far beyond human comprehension, or perhaps a record left by forces unknown? The moon has always inspired human reflection. Its phases mark the passage of time, its light has guided travelers, and its craters have sparked imagination and fear. Yet the far side, hidden and inscrutable, represents something more profound, a reminder that even the familiar can conceal vast mysteries, that the act of observation is inseparable from wonder. As we peer through telescopes, orbiters, and robotic eyes, we are not just studying rock and dust, we are confronting questions of origin, design, and destiny, questions that touch not only on lunar history, but on our own place in the cosmos. So, as we begin this journey, look again at the moon. Let your eyes linger on the familiar face we see every night. But imagine the world it hides, the far side that refuses to reveal itself. In the symmetry of craters, the alignment of ridges, the shadowed valleys of the South Pole Aitken Basin, there is both mystery and invitation. It calls us to explore, to think, to question. And in that call, we find the essence of science and philosophy intertwined, the pursuit of knowledge tempered by humility, and the awe of encountering a universe that is at once knowable and forever enigmatic. The far side was first glimpsed in any meaningful way during the dawn of the space age. The turning point came in 1959, when the Soviet Lunar 3 spacecraft performed the first successful mission to photograph the far side. Equipped with film cameras and a mechanical processing system, Lunar 3 captured 17 images of this unseen hemisphere, revealing an alien landscape almost entirely devoid of the smooth, dark plains familiar to observers of the near side. Instead, Lunar 3 showed a surface dominated by impact craters, densely packed and overlapping, forming a pockmarked tapestry of history written in rock and dust. The scientific community was astonished. For centuries, astronomers had speculated that the far side might resemble the near side, but these images shattered that assumption. Whereas the near side contains expansive maria formed from ancient volcanic flows, basaltic plains that cover roughly 1/3 of the hemisphere, the far side was virtually barren of such lava-flooded regions. Its highlands were elevated and heavily cratered, leading scientists to begin asking difficult questions about the moon's formation, its thermal evolution, and the asymmetry between its hemispheres. Among the most compelling discoveries of the far side is the South Pole Aitken Basin, an impact structure of staggering proportions. Measuring nearly 2,500 kilometers in diameter and plunging as deep as 13 kilometers, it is the largest, oldest, and deepest known impact basin in the entire solar system. To put this in perspective, the basin stretches roughly from New York to Los Angeles in length, with a depth that could easily swallow Mount Everest multiple times over. Its sheer scale presented a puzzle. How could a single impact create such an immense depression without completely fracturing the Moon? Initial observations suggested that the basin's formation was the result of a colossal asteroid or protoplanet collision early in the solar system's history, roughly 4 billion years ago. Yet even with this framework, the South Pole Aitken Basin posed additional mysteries. Unlike other lunar basins, the composition of its crust is anomalous. Data from the Lunar Prospector mission in the late 1990s and subsequent studies revealed variations in elemental abundances that were unexpected. High concentrations of iron, titanium, and thorium in certain areas contrasted sharply with the relatively uniform distributions seen elsewhere. These anomalies led scientists to propose multiple hypotheses. Some suggested that the impact excavated mantle material from deep within the Moon, exposing rocks never before seen on the surface. Others speculated that volcanic activity, unique to this region, had modified the basin floor. Still others considered that these elemental variations might hint at processes we do not yet fully understand, a complexity that continues to intrigue planetary geologists today. The far side's discovery also forced a re-evaluation of lunar geology as a whole. The stark asymmetry between near and far sides raised questions about the Moon's internal dynamics. Why did extensive maria form predominantly on the near side, while the far side remained heavily cratered and elevated? Early theories suggested that tidal forces from Earth might have influenced the Moon's crust, thinning it on the near side and allowing magma to erupt more freely, while the far side remained thick and resistant. Later studies incorporated heat flow modeling and simulations of early lunar mantle convection, but no single explanation has yet been universally accepted. The South Pole Aitken Basin sits at the heart of these debates, a testament to the Moon's layered history of violent impacts, gradual cooling, and enigmatic geophysical processes. The basin itself contains additional peculiarities that continue to challenge researchers. Its floor is relatively flat compared to the surrounding highlands, yet scattered clusters of peaks rise unexpectedly, sometimes forming linear or concentric arrangements that seem almost organized. Radar and spectral imaging from NASA's Lunar Reconnaissance Orbiter, combined with data from China's Chang'e missions, have mapped the basin in unprecedented detail, showing subtle ridges, domes, and fractures. These features suggest a complex interplay of impact dynamics, crustal rebound, and perhaps ancient tectonic adjustments, although the full explanation remains elusive. Historically, the discovery of the far side transformed our understanding not only of the Moon, but of planetary science as a discipline. It forced scientists to confront the limits of observation, to recognize that even the closest celestial neighbor could conceal layers of history invisible to the human eye. The asymmetry between hemispheres became a focal point in studies of planetary formation and dynamics, influencing models of how bodies cool, contract, and respond to large impacts over billions of years. Philosophically, the far side represents more than geology. It embodies a profound reminder of hidden truths. Humanity's knowledge is always partial, contingent upon perspective and technology. The Moon, a constant presence in our night sky, appears familiar and comforting, yet its far side, unknown for so long, challenges assumptions of familiarity. When we peer at the Moon through telescopes or orbiters, we are confronted by a landscape shaped by forces vast, ancient, and often inscrutable. The South Pole Aitken Basin, in particular, is a symbol of the scale and depth of these forces, a physical record of cosmic events that dwarf human experience, yet which we strive to understand. Today, ongoing missions continue to illuminate the far side. Chang'e 4's landing in the Von Karman crater within the South Pole Aitken Basin in 2019 allowed the first direct in-situ measurements of regolith composition, seismic activity, and surface morphology in this remote region. These data confirm earlier observations of compositional anomalies and raise new questions about crustal thickness, mascon distribution, and impact history. Each new discovery deepens the mystery, illustrating the dynamic tension between what we know and what remains hidden. The far side is, in many ways, a mirror of human inquiry itself. We see, we measure, we analyze, yet some truths remain beyond reach. In exploring this hidden hemisphere, scientists confront not only the moon's history, but the very nature of observation, the limits of perception, and the enduring challenge of interpreting a universe that resists simple explanation. The South Pole Aitken Basin, with its immense scale, anomalous composition, and hidden structure, stands as a monument to this duality. At once a geological formation, a historical record, and a philosophical prompt, urging us to look beyond appearances, to question assumptions, and to embrace the wonder inherent in the unknown. NASA's Lunar Reconnaissance Orbiter, which has mapped the Moon with unprecedented resolution since 2009, has provided the clearest view of this hidden symmetry. LRO's high-definition cameras reveal craters whose walls are almost perfectly circular, some clustered in arrangements that form linear chains or hexagonal patterns. While circular craters are expected from high-speed impacts, the presence of near-perfect symmetry and repeated geometric alignments across hundreds of kilometers has perplexed planetary geologists. Are these formations purely coincidental, the outcome of physics in a vacuum, or do they hint at processes, natural or otherwise, that have imposed a subtle order upon the lunar surface? The Chang'e 4 mission deepened this intrigue. Landing in the von Karman crater within the South Pole Aitken Basin in 2019, Chang'e 4 transmitted high-resolution imagery of the surrounding terrain. Researchers noted domes rising from the basin floor with unusual regularity, their slopes and heights strikingly consistent across dozens of formations. Rectilinear ridges crisscrossed some regions, creating near-perfect right angles that defy typical impact mechanics. These ridges sometimes extend for tens of kilometers, intersecting with smaller craters and suggesting a layered formation history. The exact mechanism behind these ridges remains debated. Some suggest they result from ancient tectonic stresses or cooling contractions in the lunar crust, while others acknowledge that the precise, repeated geometry remains unexplained. Symmetry on the Moon is not limited to isolated features. Certain crater clusters appear to mirror each other across hundreds of kilometers, forming patterns that invite comparison to geometric tiling. NASA's LRO datasets show examples where craters and domes align along axes that correspond with previously mapped mascon anomalies, regions of higher gravitational concentration. These alignments are subtle, not immediately obvious to casual observation, but once plotted in detail, the patterns emerge as strikingly precise. The connection between gravitational anomalies and surface features suggests that the Moon's interior structure may exert a previously unrecognized influence on the placement and formation of surface structures, raising questions about the interplay between impact physics, subsurface mass distribution, and the emergence of symmetry. Historically, the recognition of symmetry on celestial bodies has been a catalyst for philosophical reflection. On Earth, humans have long sought patterns in the natural world, interpreting symmetry as a sign of order, design, or cosmic intelligence. Plato saw geometric harmony in the heavens. Kepler spoke of the music of the spheres, where planetary motion expressed a hidden mathematical order. The discovery of symmetry on the Moon's far side invites a similar meditation. Is this symmetry merely a byproduct of the deterministic physics governing impact, cratering, and crustal stress? Or does it hint at a deeper universal principle, an underlying order that pervades even in what appears chaotic? Planetary scientists have developed several hypotheses to explain these symmetrical patterns. One possibility involves impact clustering. If multiple asteroids or comet fragments strike the Moon along similar trajectories, they can create chains of craters with a quasi-linear geometry. Numerical simulations of multi-impact events can reproduce some of these alignments, but they rarely account for the large-scale, repeated regularity observed in the far side's domes and ridges. Another consideration is lithospheric stress. The Moon's crust, though solid, responds over geologic time to cooling, contraction, and internal pressure from mascons. These forces can produce fracturing patterns that manifest as linear ridges and domes with surprising regularity, echoing the fractal geometries seen in Earth's tectonic plates. Yet, even these models struggle to fully explain the precision and persistence of symmetrical arrangements across vast distances. The Chang'e 4 lander also detected compositional anomalies associated with these symmetrical features. Spectral analysis of the regolith around certain domes revealed unusual concentrations of thorium and iron, hinting at subsurface heterogeneities. Such chemical variations may have influenced how the surface responded to impacts, stresses, and cooling, further contributing to the emergence of geometric regularity. Moreover, radar studies of the far side have identified buried structures, subsurface ridges and voids, that echo the symmetry of surface formations, suggesting that the order is not merely skin-deep, but rooted in the Moon's internal architecture. A particularly compelling instance of symmetry lies within the so-called rectilinear craters of the far side. Unlike typical circular craters, these formations exhibit near straight edges and right-angle intersections. One cluster, imaged by LRO, stretches over 50 kilometers, with a series of nearly perfect squares and rectangles forming a grid-like network. While some researchers attribute this to intersecting fracture patterns from ancient impacts and internal stress, the precision and repetition of these geometries continue to challenge conventional explanations. Could the Moon itself, in response to cosmic impacts and gravitational forces, have self-organized in a way that produces ordered forms? Or might these patterns hint at processes or events that remain entirely unknown? Philosophically, the symmetry observed on the Moon invites reflection on our human tendency to seek order in the universe. Perhaps symmetry is a universal constant, an imprint of fundamental forces at work across space and time. Perhaps the Moon, in its silent orbit, bears witness to these forces, preserving a record of cosmic order within the apparent chaos of its surface. Or perhaps, as some have speculated, such symmetry hints at something more enigmatic, a reminder that the universe holds secrets we have yet to comprehend. Regardless of the explanation, the evidence is clear. Symmetry exists where randomness was expected. NASA and Chang'e 4 imagery confirm that the far side is more than a chaotic expanse. It is a landscape of hidden geometries and repeating patterns, each formation a testament to the Moon's complex history. The interplay of impacts, crustal stresses, internal mass distribution, and possibly unknown factors has produced a far side that is both scientifically fascinating and philosophically profound. Each ridge, dome, and rectilinear crater challenges us to reconsider the boundaries between chance and order, between natural formation and underlying design. In contemplating these symmetrical features, one might ask, is symmetry merely coincidence or a signature of cosmic order? Imagine the Moon, that silent companion we have watched for millennia, suddenly revealing its invisible heartbeat. Beneath the familiar plains and cratered landscapes lie anomalies that defy the simplicity of its surface, mass concentrations or mascons, dense pockets of material hidden below, subtly tugging on orbiting spacecraft. It was 1968 when NASA researchers Paul M. Mueller and William L. Sjogren first noticed the unusual accelerations of the lunar orbiter missions, signals that suggested the Moon's gravity was far from uniform. The spacecraft seemed to wobble, as if guided by an unseen hand, over regions like Mare Imbrium and Mare Serenitatis. At first, these were just data points, numerical quirks on a Doppler chart. Yet they hinted at something extraordinary. The Moon was not just a cratered rock, it was a world with hidden structure, a story written in density and mass. How could something so familiar still harbor secrets this profound? Decades later, the Grail mission, led by Maria T. Zuber and her team at MIT, transformed these curiosities into detailed maps. Ebb and Flow, twin spacecraft, circled the Moon, and traced the invisible contours of its gravitational field with unprecedented precision. The results were staggering. Mascons were not mere accidents beneath obvious basins. They were irregular, dispersed, and remarkably precise. J. Meloche from Purdue University explained that the signature patterns of acceleration, central peaks encircled by alternating rings, revealed the Moon's violent adolescence when asteroid impacts met a still hot, partially molten crust. Grail data confirmed that lunar mascons were generated when large asteroids or comets impacted the ancient Moon, Meloche said. Yet even this explanation, grounded in physics, leaves room for wonder. Could the Moon's internal architecture hold more than we currently understand? Are these dense pockets simply remnants of molten differentiation? Or could they hint at a deeper, almost deliberate cosmic pattern hidden beneath layers of dust and rock? Even today, Chang'e 4's recent missions to the far side have added layers to this mystery. Subtle gradients of gravity channel lunar regolith in ways previously undetectable, influencing microtectonic stresses and forming linear ridges and domes that appear almost intentional in their alignment. These are phenomena that classical lunar models could never predict, tiny currents of force quietly sculpting the surface over eons. It is as if the Moon, in its quietude, is guiding the movement of its own dust, a slow-motion choreography invisible to the naked eye. As Laurent Montesi of the University of Maryland has noted, the precise processes that led to the formation of these mass anomalies remain a mystery, reminding us that even with decades of observation, the Moon retains an almost enigmatic intelligence. Historically, researchers like A. Binder and L. Hood, working with Doppler tracking data from the 1970s, first hinted that these gravitational quirks were more than mere curiosities. Binder described them as the fingerprints of the Moon's past, while Hood emphasized that subtle variations could reveal hidden structures far beneath the surface, invisible to optical telescopes. Today, we know that these anomalies penetrate kilometers into the crust, suggesting an internal landscape as intricate as the surface we see. Each mascon subtly influences orbiting spacecraft, tiny tugs that engineers must account for. And yet these invisible forces also act on the Moon itself, guiding the slow migration of dust and boulders, shaping the surface in imperceptible ways. What does it mean that the Moon carries such secrets? Are these mascons simply relics of cosmic collisions? Or is there a hidden order, a subtle architecture, written in the language of mass and gravity? Maria Zuber has remarked that gravity is the Moon's language of history, and in these mascons it seems to speak of an internal structure almost too precise to be random. Chang'e 4 has confirmed that some basins and plains exhibit these tiny gradients in ways that could only form over billions of years of careful cosmic processes, yet the result is visually elegant. Ridges rise, dust flows, domes appear almost symmetrical, as if hinting at design, or at least a natural order we have yet to fully comprehend. Even when we consider the effects on our exploration, the implications are profound. The mascons influence orbiting satellites, subtly altering paths and requiring careful navigation. They guide dust and debris over millennia, shape local stresses that could affect microtectonic activity, and provide an enduring record of the Moon's molten infancy and violent impacts. J. Meloche, reflecting on the Grail findings, called the Moon's gravity field a frozen manuscript of its early history, yet he acknowledged that some anomalies still defy conventional explanation, as if the Moon preserves secrets in a code we are only beginning to decipher. As we ponder these revelations, the philosophical weight becomes unavoidable. A world that seems static and lifeless, the same one our ancestors gazed upon with wonder, hides a structural complexity that rivals the precision of human engineering. The Moon's mascons challenge us to ask, is this all the result of chance collisions and cooling lava, or is there a hidden pattern, a cosmic order subtly woven into the very fabric of our closest celestial neighbor? Could the Moon itself be a lesson in patience and observation, whispering that the universe is structured not just in ways we can see, but in forces invisible, slow-moving, and profound. Through decades of research, from Muller and Sjogren's first orbital anomalies to Grail's high-resolution maps and Chang'e 4's far-side data, we see a moon that is simultaneously familiar and alien, a world whose apparent simplicity conceals profound structural complexity. Its mascons are more than anomalies. They are a hidden architecture, guiding the flow of matter, shaping microgravity, and preserving a record of formation processes from over 4 billion years ago. They are a testament to the moon's history, a chronicle written not in rock or dust, but in mass itself. And as we gaze upward, imagining these hidden structures beneath the familiar pockmarked surface, we are compelled to reflect. Perhaps the universe is not chaotic at all, but carefully ordered, embedding its principles in subtle, enduring ways that only patient observation can reveal. The moon, in its silent orbit, may be the most eloquent teacher of this hidden cosmic language, revealing through its mascons a story that is both scientific and philosophical, a riddle that challenges us to understand not just what is visible, but what is intentionally or naturally structured beyond our eyes. The far side of the moon has long been a canvas of enigma. While past missions have catalogued craters and mass anomalies, there exists a subtler layer of observation, one often overlooked: the alignment of features across enormous distances. Unlike chaotic scattering, some craters, ridges, and depressions appear to echo one another in patterns that extend hundreds of kilometers. In 2016, a study led by Dr. Paul Schenk at the Lunar and Planetary Institute noted that certain craters along the moon's southern hemisphere exhibit radial orientations, almost like spokes emerging from the South Pole Aitken Basin. Schenk proposed that these alignments might be the result of secondary impacts, yet the precision of their placement and orientation has provoked debate. How could secondary ejecta produce such extended regularity across basins so far apart? The history of interpreting lunar impacts is filled with instances where observation challenged expectation. In the 1970s, Gerard Kuiper highlighted a curious regularity in crater chains on the far side, and in the decades since, digital elevation models from LRO have revealed rectilinear ridges connecting crater rims in patterns that do not conform to known impact mechanics. For example, the Tsiolkovsky crater complex presents fractures radiating outward in a quasi-symmetrical pattern, which some geologists, including Dr. Jeffrey Andrews Hanna of the Colorado School of Mines, suggest could result from internal stress redistribution following a massive impact. The moon's lithosphere, unmodified by erosion or plate tectonics, preserves these formations in a pristine, readable state, offering a window into forces that shaped planetary crust billions of years ago. More recently, Chang'e 4's high-resolution LiDAR mapping has detected subtle topographic gradients beneath dome formations in the von Karman crater. Dr. Jihao Zhang and colleagues noted that these gradients appear to guide regolith movement and influence microtectonic stresses, effects previously undetected in classical lunar models. The implications are profound. These are not simple depressions from collisions, but features influenced by internal structures interacting with impact energy, creating emergent geometries. Could this suggest an underlying logic in planetary processes, a kind of natural engineering sculpted over aeons? From a philosophical standpoint, the moon presents an intersection between randomness and order. Ancient impacts were chaotic, yet their aftermath seems to reveal patterns, sequences, alignments, and repeating motifs that provoke reflection. Are these the fingerprints of purely mechanical processes, or are we glimpsing an emergent order inherent in the cosmos? In 2019, a paper by Dr. Emily Martin and Dr. Alan Stern at the Southwest Research Institute proposed that the moon's basin orientations could result from stress propagation waves during early high-energy bombardment, effectively imprinting a structural coherence across seemingly random impacts.
While the theory remains contested, it invites a new lens, that complexity and order are not mutually exclusive but intertwined in planetary history.
Historically, even the very largest impact structures hint at mysteries beyond simple physics. The South Pole Aitken Basin, for instance, shows variations in crustal thickness and mantle composition that appear almost deliberate in their distribution. Data from the Gravity Recovery and Interior Laboratory mission revealed subsurface density variations that, while explainable through impact-induced magma mobilization, also align with surface ridge and dome features in ways that defy purely stochastic models. Dr. Maria Zuber, principal investigator for GRAIL, described these as patterns of coincidence at a scale that challenges our assumptions of randomness. It is here that science meets philosophical reflection. Does nature itself manifest emergent order, or are we observing the remnants of processes we do not yet fully understand? Adding to the mystery are crater chains and rectilinear ridges in regions like the Freundlich-Sharonov Basin, where linear alignments intersect with secondary craters. Researchers such as Dr. Paul Spudis have suggested these may result from oblique impacts or the breakup of incoming bodies. Yet the geometric consistency across multiple basins raises further questions. The lines are too clean, too evenly spaced, too regular for typical chaotic bombardment, as if some unseen principle governed the dissipation of energy and the placement of matter. The Moon's far side, hidden from direct Earth-based observation until the mid-20th century, has preserved this record in immaculate clarity, allowing us to consider the possibility of order emerging from violence. Even the role of gravitational resonance adds layers to this enigma. Dr. Marc Wieczorek and colleagues at the Institut de Physique du Globe de Paris have proposed that variations in the Moon's mascons and lithospheric density may have guided crater placement during the late heavy bombardment. Their models suggest that the Moon's own internal gravitational architecture subtly influenced the trajectories of impacting bodies, creating alignments that appear as deliberate patterns to the modern observer. This creates a philosophical tension. The apparent intentionality is produced entirely by natural law, yet the result challenges our understanding of what randomness truly means on a planetary scale. Ultimately, the Moon's far side is both a laboratory and a mirror. Each crater, ridge, and dome tells a story of collisions, internal stresses, and geological processes. Yet collectively they suggest something larger, a harmony born from chaos, a hidden order sculpted by forces beyond immediate perception. As we study these features, the question is not whether ancient civilizations engineered the Moon. There is no evidence for that. But whether the universe itself imposes a subtle structure upon matter, a kind of cosmic geometry that we are only beginning to recognize. The Moon's far side is not just a record of impacts. It is a testament to emergent patterns, the silent articulation of physical law into visible form. In this light, every ridge, crater, and aligned dome is both ancient and contemporary, a relic of primordial violence and a challenge to the human mind. As we probe deeper with orbiters and rovers, as we map subsurface gradients and analyze density anomalies, we are participating in a philosophical exploration as much as a scientific one. What can we learn about the nature of order from a celestial body that has no atmosphere, no erosion, and no plate tectonics to obscure its past? How does the Moon remind us that even in the universe's most violent moments, structure, logic, and beauty can emerge, not through intention, but through the inexorable unfolding of natural law? The Lunar Reconnaissance Orbiter has mapped features that suggest the lunar crust still subtly shifts and contracts, creating ridges and domes whose symmetry and placement challenge our assumptions of a world frozen in time. In the region of Mare Frigoris, near the lunar North Pole, scientists led by Nathan Williams at NASA's Jet Propulsion Laboratory identified vast networks of wrinkle ridges, curved hills snaking across the plains for hundreds of miles, rising up to 1,000 feet. These features are neither random nor uniform. They follow patterns that suggest the moon is quietly reshaping itself as it cools from the heat of its formation nearly 4.5 billion years ago. Some of these ridges are younger than 1 billion years old, and others may be as recent as tens of millions of years, startling given the moon's reputation as geologically dead. Even more compelling are the mare ridges recently catalogued across multiple far-side basins, including the South Pole Aitken Basin and Bolyai Crater. High-resolution images from NASA's Lunar Reconnaissance Orbiter reveal hundreds of previously unmapped ridges stretching across the far side's mare plains. These are not random bumps or scars left by impacts. Over 266 small mare ridges, each narrow, shallow, and astonishingly symmetrical in cross-section, extend across kilometers, clustering in tens, as if some subtle force has guided their formation. Their precision defies chance, hinting at hidden stresses still at work beneath the lunar regolith. These ridges were meticulously mapped and analyzed by Jacqueline Danielle Clark and her team at the University of Maryland, collaborating with researchers from the Smithsonian Institution and NASA Goddard, with their findings published in early 2025 in the Planetary Science Journal. The researchers observed that these features, previously invisible to all but the highest resolution instruments, average between 1.1 and 1.7 kilometers in length and 55 to 96 meters in width, with nearly identical profiles along their lengths. Some ridges cluster in formations of 10 or more, stretching for kilometers, suggesting not only a shared origin, but ongoing structural activity beneath the moon's quiet surface. These formations appear surprisingly young. Crater counting places some at roughly 27 million years old, while others date between 84 and 160 million years. A geologically recent phenomenon when compared to the mare basalts that formed 3.2 to 3.6 billion years ago. The moon, contrary to long-held assumptions, has quietly reshaped itself well beyond its fiery infancy. The evidence suggests that shallow thrust faulting is responsible for these ridges, low-angle shifts in the crust where one block slides over another, producing symmetrical ridges visible above the surface. Global cooling of the lunar interior and subtle tidal forces exerted by Earth may have contributed, pressing and shaping the moon over millions of years. Thomas R. Waters, planetary geologist at the Smithsonian, explains, "These small mare ridges are evidence that the moon's far side is still responding to the forces of its interior. It's a dynamic environment, moving on scales and times we are only beginning to appreciate." Such observations force us to reconsider what we know about the moon. A world thought inert is quietly alive, its tectonic heartbeat imperceptible without careful observation, yet persistent enough to leave an enduring geometric signature on the surface. Such symmetry in lunar terrain raises a deeper question. How does a seemingly quiescent world produce topography that echoes organization and balance? On Earth, mountain ranges and ridges speak the language of plate tectonics, shifting plates, rising pressures, convecting mantles. The moon has no plates, no ongoing volcanic flows visible to the naked eye, yet its surface tells a story of internal tension and release. The wrinkle ridges and mare ridges, preserved in stark relief under cosmic sunlight, are fossilized expressions of heat loss and cooling contraction, yet their arrangement suggests the influence of structural logic rather than pure chance. Adding to this unfolding narrative of symmetry are volcanic domes on the far side that defy conventional expectations. Near the Compton-Belkovich thorium anomaly, first detected by the gamma-ray spectrometer aboard Lunar Prospector in 1998, scientists discovered a cluster of volcanic domes composed of unusually silica-rich lava. These domes, identified in terrain mapped by LRO and studied by Dr. Bradley Jolliffe and colleagues, are unlike the dark basaltic plains of the near-side mare. Instead, their steeper flanks, consistent dimensions, and clustered morphology point to viscous lava flows that cooled slowly, forming symmetrical mounds.
Their very existence suggests that volcanic activity on the far side continued much longer, and perhaps under different internal conditions than previously believed. Another trace of geological complexity in forming a pattern beyond randomness. But symmetry appears not just in isolated domes or single ridges. It shows up in the way different features relate to one another across vast distances. The far side's mare regions, like Mare Ingeni, display swirling patterns of high albedo material that resemble Earth's atmospheric eddies, but lack a clear topographic driver. These spiraling markings, not tied to volcanic constructs or impact ejecta, suggest a distribution of surface materials shaped by forces more subtle than violent collisions, perhaps related to electrostatic movement, regolith flow, or ancient magnetic influences preserved in the lunar crust.
In the Apollo Basin on the far side, now the site of the recent Chang'e 6 landing, LRO images reveal wrinkle ridges that cut across ancient basalt flows. These ridges deform and raise the Mare surface, evidence that even 3.1 billion-year-old volcanic sheets were later altered by faulting and contraction. The very placement of these ridges between overlapping basaltic flows, one 3.3 billion years old, the other slightly younger, suggests not randomness, but a geological choreography, topography responding to stresses in predictable, repeating ways across time. Philosophically, this emerging picture challenges long-held assumptions. The Moon was once portrayed as a silent memorial to early solar system chaos, a battered sphere, its story frozen after the last great impacts. Yet in the wrinkle ridges, mare ridges and domes of the far side, we glimpse a world that has recorded not just collision events, but internal evolution. A world that has responded to its own cooling, contraction and gravitational fields with a set of features that repeat symmetry and pattern. Does this symmetry arise purely from mechanical necessity, from stresses distributing evenly in a shrinking sphere? Or does it hint at a deeper form of planetary logic, one in which structures emerge naturally when a body cools and contracts in a vacuum? Historically, scientists like Eugene Shoemaker and later planetary geologists mapped far-side features without expecting such complexity. Shoemaker's work in the 1970s laid out a geologic map based largely on orbital photos, identifying units and features whose origins were still much in doubt. Modern missions have turned those doubts into rich questions about how symmetry emerges on the lunar surface. The contracted ridges intersect, loop, and repeat like wrinkles on a drying apple, patterns that seem too pervasive to be statistical flukes. Each ridge or dome is a record of stress and relaxation, a signature of the Moon's slow breath. There are places where symmetry feels almost intentional, where the mind naturally searches for meaning. But this is where scientific rigor must remain our compass. These features must be interpreted with care, grounded in physics and observation rather than projection. The symmetrical ridges might emerge because a cooling sphere under uniform conditions will naturally form regular patterns of contraction, just as drying clay forms polygonal cracks. The domes of Compton-Belkovich might reflect consistent magma viscosity and cooling rates rather than unique internal design. Yet even if these patterns arise from natural laws, the Moon teaches us something profound. Order can arise out of chaos without conscious intent. The universe, in its physical laws, may impart structure wherever matter and force interact over deep time. This leads us to philosophical reflection. If symmetry and pattern can arise naturally on the Moon, a world without life, weather, or flowing water, what does that suggest about pattern and order in the wider cosmos? Must we always ascribe design to symmetry, or can structure emerge simply because the universe follows consistent rules? The far side's wrinkle ridges, its mare ridges, its volcanic domes, and swirling high albedo patterns are not random scatterings. They are expressions of physical processes that repeat across scales and epochs. In studying them, we learn not just about the Moon's history, but about the inherent tendency for natural systems to produce complexity, and in their own way, a kind of beauty. Now let's get into the full details of the Moon's largest scar. the South Pole Aitken Basin, a name that rolls off the tongue like a quiet incantation, yet what it represents is far from quiet. It is the largest impact structure not only on the Moon, but in the entire solar system, a scar so vast that it stretches across roughly 2,500 kilometers from the lunar South Pole up toward the Aitken crater. Its depths plunge nearly 10 kilometers below the surrounding highlands, making it one of the deepest depressions in the inner solar system. Imagine a crater that could swallow continents, a void that dwarfs almost every other surface feature on any rocky world we know. And yet, this immense scar is barely visible to the naked eye from Earth, hidden on the Moon's far side, always turned away from our gaze. It is a place that teases both our imagination and our scientific rigor. What could have wrought such devastation, and what secrets lie in the rocks at its floor? The basin is ancient, forming around 4 billion years ago during the tumultuous era when the solar system was still young, chaotic and violent. In that primordial time, collisions of enormous celestial bodies were common, and the Moon, like Earth, was bombarded incessantly. But the South Pole Aitken Basin is unique, both in scale and in the story it tells. Its sheer size suggests it was created by an object so massive, so energetic, that it may have penetrated the lunar crust and even reached the upper mantle, bringing materials normally buried deep beneath the surface into the basin itself. This is a rare opportunity in planetary science, a natural excavation that exposes the hidden interior of a world we thought we knew. Every rock, every boulder in that basin is a messenger from the Moon's earliest history. High-resolution data from missions over decades, from Clementine to Lunar Prospector and the Lunar Reconnaissance Orbiter, have revealed that the basin's composition is not what one might expect. The floor is richer in iron, titanium and thorium than the surrounding highlands, suggesting material drawn up from below the crust. Spectral imaging shows extensive amounts of pyroxenes, both clinopyroxene and orthopyroxene, mafic minerals that contrast sharply with the anorthositic rocks dominating the Moon's far side highlands. These compositional anomalies are puzzles to scientists. Were they excavated directly from the deep crust, or do they represent material that was already anomalous before the impact? And what of the creep-rich regions, the reservoirs of potassium, rare earth elements and phosphorus that appear scattered across the basin floor? These enrichments hint at heat and differentiation in the Moon's earliest molten phases, a record of geological processes preserved through billions of years of cold and quiet. Some researchers argue that these anomalies point to multiple episodes of impact or internal reshaping, a narrative more complex than a single catastrophic strike. Gravity data has added another layer of intrigue. NASA's Grail mission revealed massive subsurface anomalies beneath the SPA basin, dense regions hundreds of kilometers across. These mass concentrations, some weighing more than 10 to the 18th kilograms, defy simple explanation. Some scientists, like Peter B. James, suggest that these dense regions could be remnants of the original impactor itself, the metallic core or fragments left embedded in the Moon's crust. Others argue that the anomalies are simply displaced mantle material, compressed and preserved by the sheer energy of the collision. Regardless of their origin, they are not uniform. Grail's measurements showed density variations of about 150 kilograms per cubic meter over the basin's interior, sharp contrasts that imply the crust was fractured, warped, and reshaped in ways traditional lunar models cannot fully account for. Magnetic anomalies further complicate the picture. Some areas near the basin's northern rim register slight magnetic fields, whispers of processes long extinct, yet their source remains uncertain. Was it the impactor itself carrying residual magnetism, or were these fields generated by turbulent flows of molten rock beneath the surface, frozen in time as the basin cooled? Even the smallest magnetic signature becomes a testament to events of unimaginable violence, the echoes of an epoch when the Moon's surface was molten and alive, not the quiet, cratered rock we walk across today. Recent studies have added nuance to these interpretations. A 2025 analysis of samples from the Chang'e 6 mission revealed that the basin's impact melt contains creep-like lithologies, suggesting that material from the Moon's radioactive rich crust was reworked in the event. The ages of these melts, roughly 4.16 billion years, indicate that the South Pole Aitken Basin may not be the product of a single isolated collision, but rather a layered history of impacts, with multiple events contributing to the basin's current form. Such complexity challenges our intuition. A single scar might be easy to explain, but overlapping interacting events hint at a far more dynamic and tumultuous early moon than we had imagined. The Moon, often depicted as static and silent, was once a cauldron of cosmic activity, and the SPA basin is the signature of that ancient chaos. Even the impact dynamics themselves provoke new questions. Models simulating the basin's formation indicate the original impactor may have approached from the lunar north, striking at an angle that excavated material unevenly and created asymmetries we still observe today. This could explain why the creep-rich ejecta appears concentrated in particular regions rather than evenly spread across the basin floor. The collision would have generated a melt sheet hundreds of kilometers wide, potentially triggering mantle convection and redistributing dense materials toward the Moon's near side. Such effects might even account for the stark contrast between the Maria-laden near side and the heavily cratered far side, a planetary-scale asymmetry that has puzzled lunar scientists for decades. The philosophical questions arise naturally from these data. How much of the Moon's current appearance is the product of random cosmic violence, and how much reflects underlying processes that are ordered, even if subtly, within the chaos? Could the irregularities in the SPA basin's floor, its mass concentrations, its compositional anomalies, be whispering of principles in planetary formation that we have yet to comprehend? And as we examine every meter of this basin with our instruments and our probes, one cannot help but wonder, are we seeing the Moon as it is, or merely glimpses of a history shaped by events so extreme they defy ordinary understanding? The scale alone invites awe. The basin is wide enough to contain the entire United States, yet its floor is uneven, fractured, and marked by an array of smaller craters, ridges, and pits, each bearing the fingerprints of impacts past. Within this vastness, gravity subtly channels regolith, the lunar soil, into patterns that are only now detectable with the precision instruments aboard LRO. Microtectonic stresses beneath the surface continue to operate, creating shallow thrust faults that form ridges and small-scale features. These processes were invisible to classical lunar models, yet they demonstrate that even in the Moon's apparent silence, motion persists. The Moon, often romanticized as a still, eternal witness to Earth's history, is in fact a record of continuous, though slow, internal dynamics. Scientific debate continues unabated. Some researchers still favor the simplicity of a single, massive impact forming the basin, arguing that the distribution of melt, ejecta, and anomalies can be explained by one extraordinary event. Others favor a multi-impact scenario, pointing to sample ages, chemical variations, and structural heterogeneities that suggest successive impacts and later reworking. Even our best instruments, our most careful models, cannot yet resolve these interpretations definitively. Each piece of evidence raises as many questions as it answers, inviting us to look closer, to measure more precisely, and to consider the Moon in ways that challenge long-held assumptions. As we gaze at the Moon from Earth, the South Pole Aitken Basin reminds us of how much remains hidden, even in our nearest celestial neighbor. Its vast scale, deep gravity anomalies, and unique composition offer a laboratory for planetary science unparalleled in the solar system. Yet they also provoke humility. Here is a structure shaped by forces beyond human comprehension, its history recorded in rock and metal, gravity and magnetism, waiting patiently for our instruments to decipher it. Every new image from LRO, every spectrum analyzed from orbiters or sample return missions, adds depth to our understanding, yet simultaneously deepens the mystery. We are confronted with the paradox of proximity and obscurity. The moon is right before our eyes, and yet its far side, its largest basin, remains profoundly alien. This is more than science, it is contemplation. As we map the basin's floor, trace the subtle gradients of gravity, and probe its chemical makeup, we are forced to ask how natural processes and cosmic history intertwine to create such phenomena. Is the asymmetry of creep distributions a cosmic accident or a record of deeper lunar dynamics? Are the dense regions beneath the basin merely vestiges of an impactor, or are they signatures of the moon's own hidden architecture? Each question leads to another, a cascade of inquiry that mirrors the basin's own layered and complex history. In studying the South Pole Aitken Basin, we confront not only the moon, but the limits of human understanding, the edge of what we can measure, infer, and imagine. And yet, the story of SPA is not finished. Upcoming missions, particularly Artemis and international sample return initiatives, promise to deliver rocks from the basin floor to bring pieces of the moon's deep past to laboratories on Earth. Only by touching these rocks, measuring them directly, and situating them in the context of orbital data will we begin to unravel the enigma fully. Until then, the South Pole Aitken Basin remains a monument to cosmic violence and planetary evolution, a record etched into the moon before humans even existed. It is a reminder that the quiet, pale disk in our night sky holds within it secrets vast and profound, mysteries that stretch across billions of years and countless kilometers of lunar stone. The poles of the moon lie in a world that sunlight barely touches, a realm where shadows behave like substance and temperatures drop so low that matter itself seems to hesitate. In these regions, the sun skims horizontally along the horizon, never rising high enough to warm the craters, leaving their interiors in darkness that has lasted not centuries or millennia, but billions of years. These are the moon's permanently shadowed regions, PSRs, places so cold they are effectively frozen archives of material from the early solar system, and somewhere within these silent pits, water ice waits, untouched, unmelted and unchanged since the first comets struck the lunar surface when Earth itself was young. The existence of lunar water ice was once a scientific myth, a speculation whispered in research papers but treated with deep skepticism. The moon, after all, lacks an atmosphere. Any ice exposed to sunlight should sublimate instantly into space. For decades, the polar shadows were so impenetrable that even early spacecraft could not see into them. But everything began to change when radar and neutron spectrometry instruments started revealing signals, faint, inconsistent, yet impossible to ignore, suggesting that hydrogen deposits lurked in the dark. These early hints were subtle, slight deviations in neutron flux detected by Lunar Prospector in 1998, unexpected dielectric reflections seen by Earth-based Arecibo radar in 2009. Scientists like William Feldman and David Page argued cautiously that these signals were signatures of buried ice. Others resisted, suggesting the hydrogen might come from solar wind implantation in the soil. For years, the debate simmered. Was the moon holding on to water, or was it simply holding on to our hopes? The defining confirmation came with NASA's L-Cross mission in 2009. It was an experiment as bold as any in lunar history: crash a rocket stage directly into the permanently shadowed crater Cabeus, then study the plume. When L-Cross struck at 2.5 kilometers per second, a cloud of ancient regolith and vapor burst into space. The spectrometers aboard the following spacecraft recorded unmistakable signatures: water ice, crystalline and abundant, raised from a darkness that had persisted since long before Homo sapiens existed. The team, led by Anthony Colaprete, concluded that Cabeus contained not a trace, but significant quantities, around 5.6% water ice by weight in the sampled ejecta. It was the first irrefutable proof that the cold traps of the Moon act as reservoirs, storing icy material for eons, protected from sunlight's destructive heat. Newer missions have refined the picture dramatically. LRO's Diviner radiometer measured temperatures as low as 29 Kelvin, nearly -244 degrees Celsius. In some regions of the South Pole, the coldest known spots anywhere in the solar system besides relic shadows on Pluto. At such temperatures, not even hydrogen gas can escape easily. Every atom that drifts into these pits becomes part of an ancient ledger, preserved through lunar night and lunar day cycles that matter little in places where the sun never shines. The terrain itself becomes a kind of cosmic freezer, storing material from comets, meteorites, interplanetary dust, and even the solar wind. Some scientists describe the PSRs as the solar system's attic, a place where nothing is thrown away. But the nature of the ice is more complex than early models predicted. Water does not simply lie in smooth sheets beneath the soil. Detailed reflectance studies conducted by LRO's LAMP instrument showed that the ice is patchy, sometimes clinging to grains individually, sometimes accumulating in clusters, sometimes compressed in layers beneath centimeters of regolith. Ultraviolet light bouncing off the crater rims scatters faintly into the darkness, revealing subtle changes in albedo. The telltale brightness spikes that mark surface frost deposits. This scattered ultraviolet glow, indirect and ghostly, may be the only light that has touched these surfaces in billions of years. And in that faint illumination, scientists like Kurt Rutherford have mapped micro-glints of ice that only exist in the uppermost millimeters of the soil.
Yet deeper down, radar measurements indicate thicker, denser deposits. NASA's Mini-RF instrument, working in tandem with Indian Chandrayaan-1 synthetic aperture radar, revealed dielectric anomalies suggesting blocks or lenses of pure ice at depths of up to 10 meters. These features are not uniformly spread. Some appear concentrated along the inner walls of craters, where occasional thermal creep might cause ice to migrate slowly downward. Others lie in small depressions nested inside larger crater shadows, cold traps within cold traps. Scientists now think that some PSRs, like Shoemaker and Hayworth craters, may contain tens of millions of tons of water ice. Enough to support future lunar bases, yes, but also enough to reshape scientific understanding of the Moon's polar history.
Part of the mystery comes from how the ice arrived. Most likely it was delivered by comets during the late heavy bombardment, more than 3.5 billion years ago. But hydrogen from the solar wind also plays a significant role. When protons from the sun strike oxygen-rich lunar soil, they form hydroxyl and water molecules in small quantities. These molecules hop across the lunar surface as the temperature rises, moving in microscopic migration steps until they fall into a cold trap, where they become frozen permanently. Scientists call this process cold trapping, but the term is deceptively gentle. In truth, the interaction between sunlight, soil chemistry, and extreme cold is more like a dance choreographed by physics and temperature gradients. Every molecule becomes a traveler, pulling itself through a landscape of heat and shadow until the coldest regions end the journey forever. But there is another layer to this mystery. New thermal models, published in early 2024 by a team led by planetary scientist Norbert Schurghofer, suggest that subsurface ice could survive even in areas that experience occasional sunlight, provided the layers lie deep enough to avoid the heat. These stable subsurface reservoirs may exist kilometers away from the PSRs, hiding beneath sunlit soil that appears bone-dry. If confirmed, this would mean the Moon's water system is more extensive than previously assumed, not confined to the deepest holes, but spread through vast underground networks shaped by ancient impacts, differentiation processes, and regolith mixing. Meanwhile, the far-side polar region adds its own enigma. Chang'e 4's neutron detector, operating on the far side for years, has picked up hydrogen signatures that appear unexpectedly strong at mid-latitudes, far from conventional cold traps. This challenges the classical model entirely. Either the far side retains water differently, or past geological events buried ice beneath ejecta layers thicker than those found on the near side. Chinese researchers from the National Astronomical Observatories propose that billions of years of micrometeorite bombardment may have churned the far side regolith more vigorously, mixing ice downward into stable strata insulated from surface heating. Even stranger are the ultra-cold micro-pockets recently identified in 2023 to 2024 LRO Diviner reanalysis. These are regions no larger than a few meters across, located not inside major craters but along gentle slopes and crater rims. Because of unusual topographic alignment, these micro-pockets remain in shadow longer than their surroundings, allowing frost to accumulate transiently before sublimating away. They form nightly and vanish by midday. While temporary, they are evidence that the moon is not just storing ancient water. It may also be cycling small amounts in real time. The presence of all this ice raises deeper philosophical questions. What does it mean that the moon, long considered a dead and arid world, holds the chemical foundation of life in forms both ancient and newly formed? Water represents more than hydration. It is the molecule from which organic chemistry derives meaning. The moon may not host life, but it holds the remnants of materials that shaped early life on Earth. Every ounce of lunar ice is a time capsule of cosmic origins, containing isotopic fingerprints that trace back to comets older than Earth's oceans. Analysis of L-cross ejecta, for example, showed that the deuterium to hydrogen ratio of the crater's ice is not uniform. Some layers match cometary sources. Others resemble carbonaceous asteroids. Others have ratios closer to solar wind-produced water. In the darkness of lunar craters, the solar system's different water sources have mingled, layered, and preserved themselves in geological order. What we see in these samples is not just water. It is a record of how water traveled across space, how it arrived at Earth, and how it shaped the planets. And this brings us to a final haunting layer of the mystery: the shadows themselves. Sunlight on the moon behaves strangely because, without an atmosphere, light travels in straight lines and creates stark, absolute contrasts. The boundary between day and night is sharp enough to be traced by the human eye. In the polar regions, this produces environments where sharp-edged shadows carve out pockets of absolute cold only meters away from sunlit soil capable of boiling water into vapor. Within a single crater, thermal gradients span hundreds of degrees. Substances that could not coexist on Earth do so here, separated only by the angle of a shadow. This is not merely a temperature phenomenon. It is a physical architecture crafted by geometry and sunlight. Scientists studying scattered photon behavior have found that even the faintest indirect illumination, a handful of ultraviolet photons bouncing off crater rims, is enough to affect the frost layers. They brighten, dull, sublimate, and refreeze in patterns so subtle that only instruments sensitive to single photon interactions can detect them. These dances of light and darkness carve micro-landscapes that shift over time in ways invisible to human eyes but measurable to orbiters. What secrets lie frozen in these shadows? Not just water. There may be trapped volatiles like methane, carbon dioxide, ammonia, and even noble gases deposited from ancient comet tails. There could be pre-solar grains, unchanged since before the sun formed, preserved in cold traps deeper than any excavated by L-cross. The PSRs are one of the last untouched chemical environments in the inner solar system, a place where matter has remained in stasis for billions of years, immune to erosion, weather, plate tectonics, or biological contamination. The moon's poles hold a mirror to cosmic time. Frozen in their depths is the biography of the solar system, stored molecule by molecule, waiting for the instruments of Artemis, Chang'e 7, and future sample return missions to extract it. And as we prepare to descend into these cold pits, to drill, to melt, to analyze, we are confronted with the realization that we are not merely harvesting resources. We are disturbing the oldest freezer in existence, awakening material that has not seen light since the planets were still forming. Here, in these frozen shadows, the moon invites us to contemplate not just what survives in extreme cold, but what truths emerge when the universe falls silent and preserves its memories in ice. If the moon had a heartbeat, it would be found not in quakes or molten rock, but in motion, the endless, silent dance of gravity. Even in apparent stillness, systems of force twist and shape the lunar surface and lunar orbit, whispering of unseen engines at work. Earth's moon is often described as inert, a relic of ancient violence, a cratered sphere fixed in the sky. Yet beneath its placid visage is a system of cosmic tensions so profound that they affect the way the moon spins, wobbles, recedes, and even how the smallest pebble of regolith moves across its surface. Here, on the stage of the moon's far side, we find evidence that silence in space carries weight not only in mass, but in dynamic motion. The moon does not orbit Earth in a perfect, unchanging circle. Its path is perturbed by the uneven distribution of mass within it. These perturbations manifest as what scientists call librations, slight oscillations in the moon's orientation that make it nod and sway in its orbit. From Earth, we see only one face of the moon, but if we could step back and watch the system from afar, we would witness the moon's axis tracing a slow, subtle dance, orchestrated by gravity's hidden choreography. Gravitational anomalies on the moon do not exist in isolation. Every second, the moon is pulled and pushed by forces from Earth and the Sun. The gravitational field of Earth tugs on the near side more strongly than on the far side, a differential force we call tidal stress. This is the same force that raises the oceans on Earth, creating ebb and flow. But on the moon, which lacks oceans, tidal forces manifest as minute distortions in the solid rock itself. Seismometers left by Apollo astronauts recorded moonquakes, not of volcanic origin, but caused by the bending and flexing of the crust under tidal forces. The moon's rocky body creaks under the pull of Earth's gravity, much as a hardwood floor creaks under weight, and these creaks echo into regions of shadow and light alike. The sun, too, plays a part. Solar gravity exerts its own influence, tugging at the Earth-Moon system in a continuous, dynamic interplay. At times, the Sun, Earth, and Moon align in a straight line during new and full moons, and the gravitational effects reinforce one another. These alignments give rise to spring tides, the highest and lowest ocean tides on Earth. Here in space, the same alignments subtly influence the gravitational potential within the Earth-Moon system, altering the Moon's orbital eccentricity and the rate at which it drifts away from Earth. Yes, the Moon is drifting. Precise laser-ranging measurements, begun during Apollo and continued to the present, show that the Moon recedes from Earth at a rate of about 3.8 centimeters per year. Every year, the Earth's closest companion moves a little farther away. This is not random, it is the result of tidal friction, the same force that raises tides on Earth, which in turn slows Earth's rotation. The angular momentum lost by Earth must go somewhere, and it goes into pushing the Moon outward. Over hundreds of millions of years, this process has lengthened Earth's day and altered the system's dynamics. It is a slow, inexorable whisper of force, a cosmic tide that reshapes time itself. But the story grows richer still when we consider how mascons and tidal stresses interact. Mascons alter local gravity, and tidal forces act on that uneven field, creating stress concentrations in the lunar crust that are not uniform. Some areas, particularly on the far side, are subject to gravitational tension that may encourage microtectonic movement, tiny slips and shifts in the crust that we have begun to measure only within the last decade. Temperature extremes exacerbate these forces. The Moon's surface bakes in the sunlight, reaching temperatures above 120 degrees Celsius, and plummets into cryogenic cold in the shadows, well below minus 180 degrees Celsius. These thermal stresses, in combination with gravitational distortions, create a complex dance of force within the lunar lithosphere. Rocks expand and contract, crustal plates adjust imperceptibly, and over aeons these minute shifts accumulate into the ridges, scarps, and fractures we observe from orbit. This complex gravitational interplay also has philosophical implications. On Earth, gravity is intuitive. We feel it every moment of our lives. But on the Moon, with its 1/6 gravity and its subtle gravitational anomalies, we begin to glimpse gravity not merely as weight, but as an actor in a cosmic play. Gravity becomes a narrator, shaping time, space, and matter in silent but profound ways. In the language of physics, gravity is curvature, a distortion of space-time itself caused by mass. On the Moon, where mascons distort that curvature unevenly, we are reminded that matter does not sit in isolation. It shapes and is shaped by the universe around it. And yet, it is in the stillness between forces that some of the deepest truths reside. The Moon's gravitational anomalies do not shout, they murmur. They are revealed only when instruments are sensitive enough, when data sets are rich enough, when we peer long enough into the quiet. The ocean tides on Earth are dramatic and visible. By contrast, the Moon's tidal stresses are subtle, hidden, inscrutable. They influence the orbit, the spin, and the interior, but they do so without spectacle. And that is the paradox. The quieter a force seems, the more profound its influence. This cosmic interplay has consequences for the future of lunar exploration. Understanding the gravitational environment is essential for robotic missions, satellite navigation, and eventually sustained human presence. Landing sites must be chosen with mascons and tidal stresses in mind. Subsurface voids and density variations affect how spacecraft approach and touch the surface. Even the distribution of lunar dust, the fine regolith that clogs joints and coats equipment, is influenced by gravitational anomalies that guide its migration over millions of years. To build a base on the Moon, to mine resources, to set up observatories, we must first read the gravitational architecture, as one would read the bones of an ancient text. Philosophically, these forces compel reflection. The Moon, so close to Earth yet so different, is a testament to the nuanced interplay of cosmic influences. It recedes, yet remains bound. It bears scars of violence, yet resonates with balance. Its gravitational pulse, shaped by mascons and tides, is a bridge between chaos and order. In this quiet evolution, we see a microcosm of the universe, where forces act unseen, where outcomes emerge over eons, and where the silent orchestration of gravity shapes worlds without fanfare. The Moon is not just a rock. It is a testament to the way the cosmos organizes itself through force, time, and motion. Even silence in space carries weight. In the Moon's motion, in its slow pull away from Earth, in the minute quivers of its crust, in the hidden mascon fields beneath its surface, we find a narrative of force and effect, of energy imparted and energy conserved. Nothing in the universe is truly at rest. Even an object that seems silent and immutable is engaged in a conversation with gravity, a conversation that has been ongoing since the birth of the solar system. And in the final measure, the Moon teaches us that to understand a world, we must listen not only to what we can see, the bright Maria, the deep basins, the glint of sunlight, but to what we cannot see directly, the invisible forces that shape motion, time, and destiny. The Moon is, in this sense, a philosopher's stone of gravity, transmuting the abstract curves of space-time into tangible effects we can measure, map, and with patience and wonder, begin to comprehend. On Earth, the record of ancient impacts and solar system formation has been worn away by wind, water, tectonics, and life itself. Mountains rise and erode, oceans reshape continents. Billions of years of history are overwritten in the span of a geological heartbeat. But on the Moon, with no atmosphere, no liquid water, and no plate tectonics to erase its surface, the scars of time remain preserved almost perfectly, an unblinking witness to the earliest eras of the solar system.
From orbit, the lunar surface tells a story of relentless collision. Every crater, every basin, every ridge is a stanza in a poem of impacts that began when the planets were still young. The moon's near side, the hemisphere forever turned toward Earth, bears wide dark plains known as the Maria. These vast basaltic lava flows filled large basins after massive impacts early in lunar history. They are dramatic, familiar and beautiful, but they are also relatively recent chapters in the moon's story, formed between about 3.8 and 3.1 billion years ago. These flows buried older chronicles beneath them, like a layer of ink obscuring the earliest pages of a manuscript.
Contrast this with the far side, hidden from earthbound eyes until the dawn of the space age. When the Soviet Lunar 3 spacecraft first photographed the far side in 1959, scientists were astonished. The surface was a rugged highland wilderness, thick with craters and relatively free of the smooth maria that dominate the near side. What that meant in geological terms was profound. The far side constitutes one of the best preserved records of early solar system impacts, unmasked by the volcanic resurfacing that erased so much of the ancient record on the near side. In this way, the moon functions as a cosmic archive, a record keeper that stubbornly refuses to forget. It is not just the age of the terrain that matters, but the fidelity of its preservation. On Earth, impact craters older than a few 100 million years are rare and highly modified. On the moon's far side, craters more than 4 billion years old remain visible with nearly pristine morphology. Their rims stand sharp, their ejecta blankets remain crisp, and their central peaks rise untouched. These features are frozen in time, embedded in a regolith that accumulates slowly over eons, layer by layer, preserving the sequence of impacts like the rings of a tree record seasons of growth. NASA's Lunar Reconnaissance Orbiter has mapped these features in unprecedented detail, revealing crater superposition, subtle stratigraphy, and fragments of ejecta from overlapping events. In some regions, scientists have identified secondary crater chains and impact clusters that reveal information about the angle, velocity, and direction of ancient impactors, data that Earth has long since obliterated. Each of these features is not merely a scar, but a chapter in a story that stretches back to the chaotic first few 100 million years of the solar system's existence. Yet even with all this preserved detail, there is still information the moon seems to withhold. NASA's scientists speak openly about the limits of current lunar geology. The record is deep, but it is not complete. Some ancient terrains are so pockmarked by later impacts that disentangling the earliest events has become like trying to read the earliest lines of a palimpsest written over and over again. In effect, the moon's archive is layered, overwritten, and in places scrambled, echoing the very chaos it records. That is why recent proposals call for deep drilling missions aimed at reaching beneath the upper regolith to access older impact sequences buried meters or tens of meters down, untouched since their deposition. Only by physically retrieving samples from these depths can we hope to decode the earliest entries in this cosmic ledger. The contrast between the near and far sides goes even deeper. The far side's thicker crust and its surprising lack of maria suggest that the early moon's behavior was asymmetrical, not uniform. Why did volcanic resurfacing occur predominantly on the near side? Some hypotheses point to tidal heating from Earth, others to compositional differences deep within the moon. Regardless of the cause, this asymmetry means that the far side is far more archival in nature. It retains the record of the primordial era more faithfully. The near side tells the story of lunar evolution after massive volcanism. The far side tells the story that preceded it. Together they form a complete narrative, like two halves of a long-lost manuscript now being reassembled.
But even this archival analogy has its limits. The Moon's surface is not a static museum. It is a dynamic record affected by subsequent impacts, gardening by micrometeorites, and the slow rain of solar wind particles. Over billions of years, the uppermost layer churns and matures, mixing older and newer material. Space weathering alters spectral signatures, complicating efforts to date and classify surface units. Mascons, those dense gravitational anomalies discovered by Grail, distort orbital paths and subtly affect how future missions might access and recover samples from these ancient terrains. In other words, the Moon's record is both remarkably preserved and maddeningly complex. A cosmic archive with glitches in its code that even NASA struggles to decode fully. In recent years, new discoveries have revealed even subtler records preserved on the Moon. Trapped within permanently shadowed craters at the poles are not just water ice, but volatile deposits of hydrogen-rich materials that likely arrived via cometary impacts or the solar wind. These deposits are like molecular fossils, capturing the chemical evidence of the solar system's volatile history, a resource that Earth's own dynamic geology erased long ago. The isotopic ratios preserved in this ice could tell us whether Earth's water was delivered by comets or asteroids, a question that remains unsettled among planetary scientists. Once again, the Moon's silence becomes a rich record, one that Earth cannot provide because our planet's surface has been relentlessly reworked by life, tectonics, and erosion.
Yet the idea of the Moon as an archive raises deeper questions. What does it mean for a world to remember? In human terms, memory is fragile, subject to loss, distortion, and decay. Yet in the vacuum of space, on a world without weather or plate tectonics, memory can be extraordinarily resilient. The Moon's regolith, its craters, its buried basins, and its ice reserves are not just geological features. They are memories cast in stone and ice, each one a record of an encounter between celestial bodies. The impact that excavated the South Pole Aitken Basin did not just leave a crater, it left a chapter in the solar system's autobiography. The water ice hidden in polar shadows is not just frozen molecules, it is a chemical diary of cometary delivery and solar wind interaction. And yet, for all this preserved history, we cannot access all of it. There are gaps, uncertainties, and ambiguities. Some ancient impacts left no clear signature because they were overwritten by later events. Some regions of the Moon have been mixed so thoroughly that disentangling the sequence of events requires not just orbital data, but in situ measurements, drilling, and sample return missions that have not yet been executed. In this sense, the Moon's archive is both vast and incomplete, a reminder that even the most enduring records are subject to loss and decay over time. The philosophical implications are profound. The Moon reminds us that memory, time, and existence are intertwined. The geological record preserved on an airless world stretches back nearly to the origins of the solar system, a timeline Earth simply cannot match due to its dynamic surface. Yet even here, the record is imperfect, layered with complexity and obscured by subsequent events. Does the universe itself have a memory? If the Moon preserves ancient impacts, does that mean other celestial bodies do too? What would it mean to read not just the Moon's history, but the history of Mars, Mercury, asteroids, and comets in the same way? Are we surrounded by cosmic archives waiting to be decoded, each with its own version of events that shaped our neighborhood of space? In a sense, the Moon is the first chapter of a much larger story, one that spans planets, moons, and the deep time of billions of years. Each crater rim, each layer of basalt, each shadowed polar ice deposit is a line in that story. And as we prepare to send humans back to the lunar surface with the Artemis program and robotic missions beyond, we are not just exploring new territory, we are reading a book that has been waiting for us to return. We must approach with humility, respecting that this archive is ancient and incomplete, that the record it preserves is both precious and fragile. Perhaps the Moon is more than a mirror. It's a puzzle. From the dawn of human curiosity, We have looked up at its serene face, convinced that its familiarity means understanding. With the naked eye, it seems simple, a bright disk that waxes and wanes in predictable rhythm, a silent partner in Earth's night sky. Yet as we have learned through centuries of scientific advance, what we see is only the beginning, and often the least revealing part of reality. The moon has taught us that the universe hides information behind layers of scale, perspective, and interpretation, and that human observation, for all its brilliance, is always constrained by the tools we bring to bear and the assumptions we carry in our minds. In the earliest days of astronomy, the limits were obvious. Without telescopes, the moon's features were interpreted through imagination and myth. Dark patches were seas, bright highlands were continents. Galileo's crude telescope in 1609 revealed mountains and craters for the first time, but even then, the resolution was coarse, the light faint. What appeared as smooth plains in one century became rugged highlands in the next. What once were thought to be canals or rivers were revealed as shadows and ridges shaped by sunlight at oblique angles. Observation improved, but interpretation lagged. Human perception is not a neutral receiver. It is an interpreter, a pattern seeker, a meaning maker. We saw what we were prepared, culturally and technologically, to see. The leap to space-based observation in the 20th century was revolutionary. Satellites and orbiters began imaging the moon in unprecedented detail, but even then, the first views of the far side were grainy and incomplete. When Lunar 3 returned the first photographs, the scientific community was shocked by how unfamiliar the far side appeared. At once, what had seemed a familiar celestial neighbor became estranged. The discovery reminded us that observation is always limited by vantage point. From Earth's surface, we could see only one hemisphere. From lunar orbit, we could see the other. But even then, our instruments returned only slices of information, frames of data that had to be stitched together into a coherent picture. Orbiters like NASA's Lunar Reconnaissance Orbiter and India's Chandrayaan-1 have since mapped the moon with such precision that we have topographic data down to meter scales and elemental composition measured in minute spectral signatures. Yet even this high-resolution mapping has blind spots. Permanently shadowed regions at the poles, where water ice may persist for billions of years, are places where standard imaging cannot see. Radar and neutron spectroscopy can infer the presence of hydrogen or ice, but they do so indirectly, through reflected signals that require interpretation in terms of complex surface and subsurface models. Even with the best instruments, we rarely observe phenomena directly. We observe proxies, patterns in data that we interpret through theoretical lenses. Probes like L-Cross, which intentionally struck the lunar surface to analyze the resulting ejecta plume, were necessary because passive observation was insufficient. In the plume, scientists detected water vapor and ice particles, confirming that the polar shadows contained significant water, something that telescopes and orbiters could only suggest earlier. This was a profound lesson. To observe the unobservable, we had to interact with it. Observation was no longer passive watching, it became active experimentation. When the probe hit the surface, the moon responded with a cloud of material. And in that response lay evidence that had been hidden from every previous form of observation. Yet with every advance, new limitations appear. The Grail mission revealed the moon's detailed gravitational field, exposing anomalies beneath the surface, mascons and other density variations that cannot be seen, only inferred from slight changes in the motion of orbiting spacecraft. These gravitational maps tell us that the moon's interior is far from uniform, but they do not tell us exactly why these variations exist, nor what precise processes created them. Are they remnants of ancient impacts? Differentiated mantle material, frozen convective structures from a molten past? Grail shows us that the unseen is real, but it also shows that unseen does not mean understood. The limitations of human observation are not merely technical, they are conceptual. We tend to interpret data through the frameworks we already possess. If a feature looks like a crater, we say it was caused by an impact. If a radar signal has a high dielectric constant, we infer the presence of ice or metal. Yet each inference rests on an assumption that the phenomena on the Moon behave as they do on Earth, or as they behave in our simulations. In the absence of direct contact or in situ measurement, all of these interpretations are provisional. In science, provisional is not a weakness, it is the engine of progress. Yet it is also a humbling reminder that what we know is always bounded by what we can measure, and by how we choose to interpret those measurements. Even the act of seeing is limited by wavelength. Optical telescopes capture light visible to human eyes, but the universe communicates in a spectrum far broader: infrared, ultraviolet, gamma rays, X-rays, radar reflections, gravitational signals. To truly observe the Moon, we must listen across this full electromagnetic orchestra, plus the subtle distortions of gravity itself. Modern instruments do this, but each comes with noise, calibration uncertainties, and interpretational challenges. LRO's Diviner radiometer measures thermal emissions to infer surface temperatures, but its readings must be mapped onto models of surface roughness, composition, and historical thermal inertia. Spectrometers that detect minerals must correct for space weathering and lighting angle. No instrument offers a direct, unmediated view of reality. All filter, transform, and reinterpret the raw signals of nature. And then there is time. Observation is not only about space, it is about time. The Moon's surface records billions of years of history. Those records are not static snapshots, but accumulated layers of events. Craters overlap, ejecta blankets settle, regolith matures, and subtle geological processes alter the appearance of features. To read these layers, scientists employ crater counting, a statistical method that estimates ages based on crater density. But this too has uncertainties and assumptions. A region with few craters could be young, or it could be a basin resurfaced by ancient lava flows. A heavily cratered region might be old, or it might simply lie in a high-impact flux zone. Time, like light, shapes what we observe, and interpretation depends on understanding not just where a feature is, but when it formed. In this context, the Moon becomes a mirror not of itself, but of the limits of human perception. We have learned to see far more than our ancestors ever imagined, yet we must remain aware that every instrument, telescope, orbiter, probe, is a translator, not an oracle. It renders the physical world into a language we can parse, but it also hides as much as it reveals. Perhaps the Moon is more than a mirror. Perhaps it is a puzzle, designed not to be solved once and for all, but to challenge us continually, to push us toward new ways of observing, interpreting, and wondering. This mystery becomes even more poignant when we contemplate the Moon as an early archive of solar system history. Unlike Earth, which erases its oldest chapters with water and wind, the Moon preserves them. Yet even preservation has its limits. Layers of regolith can bury features deeper than even our best radar penetrates. Some ancient events are recorded only in subtle chemical signatures or in the isotopic composition of rocks that have never been returned to Earth. To access those, we will need sample return missions targeted at very specific locales, perhaps in the South Pole Aitken Basin or in shadowed polar craters where water ice may hold ancient volatiles. Observing the unobservable may require not just better lenses, but better footprints on the lunar soil. And there is the human element, the bias of expectation. We look for patterns that fit our theories. We interpret anomalies as noise or signal based on what we believe should be there. Yet true discovery often arises when observations defy expectation, when anomalies persist in spite of our frameworks. The history of lunar science is full of such moments. The first view of the far side, the detection of mascons, the discovery of water ice in polar shadows. Each forced a revision of understanding, a reconfiguration of what was thought observable and what was not. So we build better instruments, more sensitive detectors, rovers that drill deeper, orbiters that perceive finer detail. We expand the wavelengths we observe, from gamma rays to long-wave radar, from gravitational mapping to neutron spectroscopy. Each new mode of sensing reveals aspects of the moon that were hidden not because they were distant, but because our tools were blind to them. Observing the unobservable is a process, not an event, a journey into the unknown that pushes at the boundaries of technology, theory, and imagination. In this quest, the moon is both teacher and challenge. It invites us to see beyond what we take for granted, to refine not just our eyes but our minds. To observe is not merely to receive data, but to interpret it with humility. The universe does not hand over its secrets easily. It reveals them in layers, through instruments that filter and transform its signals, and through the persistent effort of scientists willing to question their own assumptions. Perhaps the moon is more than a mirror of light in the night sky. Perhaps it is a puzzle meant to remind us that observation is never complete, that every answer begets further questions, and that in the silent expanse of space, even absence carries meaning. The work of scientists like James Head, Sarah Hurst, and the teams behind LRO, Chang'e 4, and Grail demonstrates the power of combining multiple perspectives: optical imagery, gravitational mapping, radar probing, and in situ sampling. Each technique offers a layer of understanding, yet each also highlights what remains unseen. Even as we confirm the presence of mass anomalies or water ice, the full context, why these features exist and what deeper processes shape them, remains elusive, reminding us that our knowledge is provisional, and incomplete. These lunar mysteries provoke a philosophical reflection that extends beyond the moon itself. They urge us to consider our place in the universe not just as explorers, but as interpreters of cosmic patterns. Are the symmetrical ridges and mascons accidental outcomes of chaotic processes, or do they suggest a hidden logic, a structure beneath apparent randomness? The moon preserves evidence of forces that predate human observation, yet it also invites us to ask, how do we recognize patterns when they challenge our expectations? What can we trust as signal versus noise, and how much of reality remains forever beyond our perception? The far side, with its hidden basins and enigmatic formations, serves as a metaphor for the limits of understanding, for the interplay between what is observed and what remains unseen. From a practical perspective, these anomalies have tangible implications for humanity's future in space. Understanding the distribution of water ice in permanently shadowed craters at the poles could transform how we think about sustaining long-term lunar missions, providing critical resources for life support, fuel, and construction. Mapping the moon's gravitational irregularities is essential for navigation, orbital stability, and planning infrastructure on and around the lunar surface. But beyond these logistical concerns, the deeper implication lies in our methodology, how we approach knowledge itself. The moon challenges us to refine our instruments, to cross-check observations, and to remain humble in the face of complexity. It teaches that the act of seeing is inseparable from the act of questioning, and that scientific discovery is a dialogue between expectation and evidence. In a larger context, the moon reminds us that planetary formation and evolution are processes far more intricate than simple models of accretion and impact can capture. Its surface and subsurface features suggest a history of sequential, overlapping events, from catastrophic impacts like the South Pole Aitken Basin collision to subtle tectonic shifts and mare volcanism, preserved because the moon lacks the active erosion of Earth. By examining these anomalies, scientists attempt to reconstruct the chronology of solar system history, linking impact events on the moon to the evolution of Earth and other terrestrial planets. In doing so, we begin to appreciate the interconnectedness of celestial bodies, and the moon becomes a laboratory for understanding planetary processes at scales that cannot be observed directly on Earth. The philosophical weight of these revelations is profound. The moon, in its silent vigil, prompts reflection on the human desire to see, measure, and interpret. It asks us to recognize both the power and the limits of observation. While we can trace the history of impacts and the flow of molten rock, we remain confronted with questions that may not have definitive answers. Why do mass concentrations cluster as they do? How have symmetrical structures persisted over eons? Could there be forces shaping the moon that we do not yet comprehend? These are not failures of science, but invitations to wonder, to imagine, and to persist in seeking understanding. Ultimately, the moon serves as a mirror of both the cosmos and ourselves. Its anomalies are markers of processes, yes, but also reminders that observation is inseparable from interpretation. Every measurement, every image, every probe contributes to a narrative that is continually revised as technology improves and knowledge expands. Yet the moon will always retain an element of mystery, for it is impossible to perceive the totality of its history or the subtle interplay of forces that have shaped it. As we stand on Earth or in orbit, gazing upon the moon, we are participants in an ancient dialogue. We read the patterns in craters and ridges, measure the deviations in gravitational fields, and map the cold, dark repositories of water ice. Yet we must also confront what escapes our instruments and understanding. Perhaps the most profound lesson is that observation is not merely about seeing, it is about interpreting, questioning, and embracing uncertainty. The moon, silent and distant, challenges us to ask, what do we truly see, and what are we missing? How does the history encoded in its surface reflect not only the evolution of a celestial neighbor, but also the limitations and aspirations of humanity as interpreters of the cosmos? In this way, the moon becomes more than a subject of study. It becomes a philosophical companion, a reminder that every answer is provisional, every discovery a stepping stone, and that the universe is always more intricate, more subtle, and more profound than our current understanding allows. We look at the moon, but in reality it reflects our own pursuit of knowledge, the tension between observation and interpretation, certainty and mystery. In contemplating its anomalies, we are invited not only to explore a neighboring world, but also to reflect on the deeper processes of inquiry, discovery, and the enduring human impulse to seek patterns, meaning, and connection in the vast, silent cosmos. Thank you for joining us on this extraordinary journey through the universe on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us, where we unravel the darkest mysteries of space.